What if the great silent darkness between the stars is not empty at all? For millennia we have looked out into that void and felt a profound sense of isolation, believing our solar system was a secluded island adrift in an endless cosmic ocean. We saw the stars as fixed and distant points of light, their planetary systems forever beyond our reach and ours beyond theirs. We were, we thought, utterly alone in our little gravitational harbour, sheltered from the vast currents of the Milky Way. All of our stories, our science, our understanding of our place in the universe were built upon this foundational belief in our splendid separation. Then, in the autumn of 2017, something appeared that shattered that illusion forever. It was a phantom, a whisper from the deep, a tiny point of light moving so fast and on such an impossible trajectory that it could only have come from one place, the interstellar abyss. Astronomers named it Oumuamua, a Hawaiian word for scout, a messenger from afar. It was our planet's first confirmed contact with an object forged in the crucible of another sun. For 74 days it held the world's scientific community in a state of captivated disbelief as it tumbled through our cosmic neighbourhood. It was nothing like the comets or asteroids born and raised in our own solar system. It was small, dark red and elongated, perhaps 10 times longer than it was wide, a bizarre cosmic needle threading its way through our skies. It spun like a thrown bottle, its brightness fluctuating wildly with every rotation. Most unsettling of all, it didn't just follow the elegant curves of gravity dictated by our sun. As it began its long journey back out into the void, it gently, inexplicably accelerated. Something was pushing it, a subtle, persistent force that defied our models. There was no visible tail of gas and dust, no cometary outgassing to explain its strange celestial defiance. It was a ghost ship, silent and dark, powered by an invisible wind. We aimed our most powerful telescopes at it, desperate to understand its nature, but it was already receding, a fleeting enigma shrinking back into the darkness from which it came. Oumuamua left us with a tantalizing and deeply unsettling legacy of questions. What was it? A new kind of comet? A shard of a shattered alien planet? Or something else entirely? The debate raged, pushing at the very boundaries of established science. Oumuamua was a cosmic riddle, a single confounding data point that hinted at a universe far stranger than we had ever dared to imagine. Just 2 years later, a second visitor arrived, tearing through the constellation of Lynx. This one was named 2I, Borisov, after its amateur discoverer. And at first it seemed to be the answer to our prayers, the missing piece of the puzzle that would put Oumuamua into context. Borisov was different. It was enormous, a hulking mass of ice and rock trailing a magnificent ghostly tail of gas and dust that stretched for 100,000 miles. It looked for all intents and purposes like a classic comet. A comet, yes, but one that was unequivocally not times ours asterisk. Its chemical signature, its isotopic ratios were subtly but profoundly alien. It was a piece of another solar system, confirming that the building blocks of worlds like ours were likely common throughout the galaxy. In many ways, Borisov was a comforting discovery. It suggested that interstellar space was populated by objects we could understand, that the laws of physics and chemistry were consistent across the void. It was the normal that made Oumuamua's profound weirdness all the more glaring. Borisov proved that Oumuamua was not a fluke. The interstellar highway was real. Our solar system was not an island but a crossroads, a temporary port of call for celestial pilgrims on journeys of unimaginable length. We were no longer alone in our harbour. The currents of the galaxy were flowing right through our home, carrying messages in bottles from shores we have never seen. The hunt was now on. With 2 confirmed visitors, we knew there had to be more. Observatories around the globe recalibrated their search protocols, their algorithms trained to spot the telltale trajectories of these cosmic wanderers. The great digital nets were cast wider than ever before, sifting through the nightly cascade of data for the next traveller. We were ready. We were watching. We thought we knew what to look for. And then, on a cold night in late December, a robotic eye on a Hawaiian mountaintop flagged another one. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, is a network of telescopes designed as our planetary defense system, a silent guardian scanning the skies for any threat heading our way. Its software is programmed to find the unusual, the object that doesn't belong. And on that night, it found a faint, unassuming smudge of light moving against the stellar background. The initial alert was routine, another potential near-Earth object to be tracked and catalogued. But as observatories around the world turned their gaze to corroborate the finding, a different story began to emerge from the numbers. The calculations poured in, tracing the object's path backward in time, beyond the orbit of Neptune, past the Kuiper Belt, out into the cold, dark frontiers of our solar system. The numbers didn't curve back on themselves. They didn't form the closed elliptical loop of a body gravitationally bound to our sun. They formed a hyperbola, a sweeping, open-ended arc that pointed like an arrow straight out into the interstellar deep. This was it. Interstellar object number 3. We had found another one, catalogued as 3I, Atlas. It was a triumph for the new era of astronomy. It was proof that our methods worked, that we could now reliably detect these messengers. For the first few weeks, it behaved exactly as we expected an interstellar comet to. As it fell toward the sun, the warmth of our star began to sublimate its ancient ices. A faint, glowing atmosphere, a coma began to form around its nucleus, growing brighter with each passing day. It looked like it would be another Borisov, a familiar and welcome guest. It was a chance to gather more data, to refine our models, to add another piece to the growing mosaic of our understanding of the galaxy. It offered a sense of comforting predictability, a feeling that we were finally getting a handle on this new and profound cosmic reality. We believed we were witnessing a routine celestial event. We were profoundly, catastrophically wrong. We were not prepared for an object that would not just challenge our theories, but break them. We were about to witness an event so precise, so baffling, and so utterly impossible that it would force us to question the very distinction between a natural phenomenon and a deliberate act. As 3I, Atlas, continued its inexorable plunge toward the inner solar system, something began to change. The world's most powerful telescopes, including the Hubble Space Telescope, were fixed upon it, tracking its every move, dissecting its every photon. Astronomers noticed its nucleus was not brightening steadily. Instead, its light curve began to fluctuate erratically, a sign of instability. The object was becoming agitated. We had seen this before. Comets, especially those making their first fiery pass around a star, are fragile things. The thermal shock and the sun's immense gravitational pull can be too much for their loosely packed structures of ice and dust to bear. They can and often do break apart. So when the data first suggested that 3I Atlas was beginning to fragment, there was no immediate alarm. It was a fascinating development, certainly a chance to watch the death of an alien comet in real time. We anticipated a messy, chaotic disintegration, a puff of dust, a spray of uneven fragments tumbling away from each other, a slow and spectacular fade into nothingness. It would be a dramatic but ultimately understandable end. But what Hubble saw next was not understandable. It was not chaotic, and it was not natural. On a series of crisp, clear images taken over several days, we watched the heart of 3I, Atlas, perform an act of impossible celestial choreography. It did not explode. It did not shatter into a cloud of random debris. Instead, with a precision that sent a tremor of disbelief through the entire astronomical community, the nucleus cleanly and deliberately separated. One object became 3. They were not jagged shards. The telemetry showed 3 distinct, well-defined, and most unnervingly of all virtually identical components. They moved away from each other with a slow, gentle grace, maintaining a perfect, almost geometric separation. It was less like a fragmentation and more like an unfolding. It wasn't the violent death of a comet. It was the serene, controlled deployment of a tripartite system. Imagine a piece of ancient stone placed under immense pressure, fracturing along its natural fault lines into 1,000 different shapes and sizes. That is what a natural breakup looks like. Now imagine that same stone touched by an invisible force, splitting cleanly into 3 perfectly polished, identical spheres that then drift apart in perfect unison. That is what we witnessed in the heart of our solar system. It was an event for which we have no name, no theory, no explanation. The data was checked, the instruments were recalibrated, the images were processed and reprocessed. There was no error. It was real. The implications began to sink in, and a quiet, profound wave of awe and consternation swept through research institutions around the world. The serene beauty of the event was matched only by its sheer physical impossibility. Let us be perfectly clear about the problem this poses, for it is the central mystery that drives our entire investigation. There is no known natural mechanism that can account for what we saw. None. Tidal forces from the sun, the gravitational stretching that can rip a body apart, would have produced a messy, elongated string of debris, not three uniform pieces. The rapid sublimation of ices, creating jets of gas that can spin a comet apart, would have resulted in an asymmetric, chaotic tumble, sending fragments flying off at different speeds and on different trajectories. A collision with another smaller object would have created a spray of countless variably sized chunks. Every single scenario that physics can offer predicts chaos, asymmetry, and randomness. What we observed with 3I, Atlas, was the polar opposite order, symmetry, and precision. It was as if a cosmic geode had been opened, not with a hammer but with a jeweler's saw. This single, silent event, which took place hundreds of millions of miles from Earth, has presented humanity with the most profound question it has ever had to face. It is a question that straddles the line between science and philosophy, between observation and belief. When we witness an event in the cosmos that so flagrantly violates every known law of nature, what are we left to conclude when the universe presents us with an object that behaves not like a random piece of rock and ice, but like a piece of sophisticated functioning technology? How are we supposed to react? The perfect tripartite split of 3I, Atlas, has moved the conversation beyond the realm of unusual comets and into territory once exclusively reserved for speculation and fiction. It forces us to confront a possibility that is as terrifying as it is exhilarating, that the object we tracked was not just a messenger from another star, but a message. We have been left with a celestial artifact, a calling card from an unknown intelligence, and the monumental task of deciphering its meaning. The journey to understand what happened to 3I, Atlas, is more than just an astronomical investigation. It is a quest that will take us to the very limits of our knowledge, forcing us to re-examine the foundations of physics, chemistry, and biology, and to confront the deepest and most enduring question of all. Are we alone? The evidence now, floating in our own solar system, suggests an answer, and that answer may change everything. For all of human history, the night sky was a room with a locked door. The sun, the moon, the planets, the comets that blazed across our field of vision, they were all part of the same celestial family, our family. They were born with our sun forged from the same spinning disk of primordial dust and gas, forever bound by the invisible tether of its gravity. Everything we could see, everything we could study, was a reflection of ourselves, a piece of our own cosmic heritage. We believed, entirely alone in our cosmic neighborhood. The vast star-strewn gulfs, separating us from even the nearest suns, seemed impassable, a silent, empty moat around our solar system's castle. No messages could cross it, no travelers could survive it. The idea that a physical object, a rock or a chunk of ice from a world circling another star, could journey for millions, perhaps billions of years through that unforgiving emptiness and happen to stumble into our tiny gravitational well was the stuff of pure fantasy. It was a statistical impossibility, a dream reserved for poets and writers of fiction, not for the serious minds of science. Then in the 21st century we found the key. We didn't just unlock the door, we blew it clean off its hinges. The key wasn't a single brilliant discovery, but a revolution in perception. It was the birth of automated robotic eyes, tireless sentinels that stared into the dark so we no longer had to. Among these new guardians, one network stood preeminent: Atlas, the Asteroid Terrestrial Impact Last Alert System. Its name speaks of a terrestrial purpose, a shield against threats from within our own system. But its unblinking gaze, sweeping the entire observable sky every few nights from its perches in Hawaii, Chile, and South Africa, was fundamentally agnostic. It did not care where an object came from. It cared only that it moved. Atlas is not a single monolithic telescope in the traditional sense. You should instead picture it as a planetary nervous system, a web of relatively small, powerful instruments working in perfect unison. Each night as the Earth turns its face from the sun, they awaken. They don't hunt for specific famous targets. They simply drink in the entire sky, capturing billions of pinpricks of light in immense digital photographs. This is where the magic and the immense challenge truly begins. An automated river of data, a torrent of cosmic information so vast it would overwhelm any human observer, flows from these telescopes to powerful processing centers. Sophisticated algorithms, the unsung heroes of this new age, immediately get to work. Their task is monumental to compare tonight's sky with the sky from 2 nights ago and the sky from the week before that. They are searching for the tiniest deviation, for anything that has changed its position against the static backdrop of distant stars. Most of what they find are our neighbours' known asteroids on their predictable orbits, a newly spotted comet from our own Oort cloud, or even the fleeting glint of our own man-made satellites. The software dutifully catalogues these familiar motions, filtering out the 99.999% of things that belong to us. It is programmed, however, to flag an anomaly. It is designed to notice when something is not just moving, but moving wrong. When an object's path through our heavens defies the elegant elliptical laws that govern everything orbiting our sun. When it is moving too fast on a trajectory so steep, so extreme that it screams of a single astonishing truth, it isn't falling times around times our sun. It is simply falling times past times it. This is the celestial tripwire, the digital net we finally cast wide enough to catch a ghost. And in 2017, the net twitched. For the first time in history, we caught one. It was a bizarre, confounding object eventually named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The name was perfect. It was the first confirmed visitor from another star system, a true interstellar object, and it was deeply, profoundly weird. It was small, dark and tumbling end over end. It was shaped, astronomers deduced, less like a sphere and more like a cosmic needle or a flattened shard, unlike any asteroid or comet we had ever seen. Most unnervingly, as it swung around the sun, it gently accelerated away, pushed by a mysterious force that wasn't gravity. There was no visible tail, no gaseous jet of sublimating ice to explain the push. It was a genuine enigma, a riddle sent from the void that sparked a firestorm of debate and speculation. Was it a new kind of natural object we couldn't comprehend? Was it, as some daringly proposed, something more? Oumuamua didn't give us time to find out. It shot back out into the darkness as quickly as it came, leaving us with more questions than answers and a burning hunger for the next visitor. We had proven interstellar objects were real, but the first one only deepened the mystery. 2 years later, the net twitched again. This time the catch was different. This object, designated 2I, Borisov, was comforting. As astronomers trained their instruments on this second interstellar traveller, a collective sigh of relief seemed to pass through the scientific community. Borisov looked and behaved exactly like a comet. It was a large, dirty snowball, just like the ones from the frigid outer reaches of our own solar system. As it neared the sun, its ices began to vaporize, shrouding it in a beautiful ethereal cloud, a coma, and sprouting a long, majestic tail. Its chemical composition, when analyzed from afar, was familiar. Its behavior was predictable. Borisov was the proof we needed that Oumuamua wasn't the universal standard. It demonstrated that normal, comprehensible objects, the kind our theories predicted should exist in abundance, were also drifting through the interstellar dark. So now we had a framework, a set of 2 opposing goalposts for what an interstellar object could be. On one end, you had the bizarre physics-defying mystery of Oumuamua. On the other, the reassuring textbook familiarity of Borisov. The stage was set. The scientific world was primed, eagerly awaiting the third visitor, wondering which category it would fall into. Would it be another confounding puzzle, or another piece of welcome confirmation? On a cold night in early 2021, the digital sentinels of Atlas once again sounded their silent alarm. Deep within the torrent of data, the algorithms flagged a new point of light. It was impossibly faint, a mere whisper against the noise of the cosmos located in a patch of sky within the constellation Andromeda. To the human eye, it was nothing. To the machine, it was a suspect. The initial observation was automatically logged, and as the Earth continued its spin, other telescopes were alerted. Follow-up observations were critical. A single data point is just a dot, two make a line. But 3, 4, 5 data points, they begin to tell a story. They trace an arc, and the arc being traced by this faint smudge was unmistakable. It was not a gentle looping ellipse, the familiar signature of an object tethered to our sun. It was a hyperbola, a fierce open-ended slash across the fabric of our solar system. The geometry was brutal and definitive. This object was moving with such tremendous velocity that our sun's gravity was little more than a temporary inconvenience to it. It would curve in slingshot around our star and fling itself back out into the void, never to return. It was a tourist, not a resident. It was visitor number 3. The object was provisionally designated C 2021A 3, but its true identity was already clear. It would soon be coronated with the formal designation 3I, Atlas, signifying the third confirmed interstellar object discovered by the survey that bore its name. As observatories around the globe began to pivot their massive mirrors towards it, the initial findings painted a picture of comforting normalcy. Spectroscopic analysis, the technique of breaking down an object's light to read its chemical fingerprint, suggested the presence of water ice and other volatile compounds. Through the lenses of powerful telescopes, it appeared as a small, fuzzy patch. A coma was clearly developing around a central nucleus, a telltale sign of a comet awakening from a long, cold slumber. As it journeyed closer to the inner solar system, the sun's warmth began to act upon its surface just as it had with Borisov. The faint cloud around it grew larger, brighter. A nascent tail, a ghostly streamer of dust and gas, began to trail behind it. Everything about it, from its trajectory to its appearance to its preliminary composition, placed it squarely in the Borisov camp. It was a classic comet by all accounts. An exciting object, to be sure. Any visitor from another star is a priceless scientific treasure, but it was an understandable one. Scientists began to build their models, their predictions for its journey. They calculated its path with exquisite precision, forecasting exactly where it would be in the sky on any given night. They estimated how its brightness would increase as it approached perihelion, its closest point to the sun. It would become a tantalizing, though likely faint target for amateur astronomers, a fleeting guest from an unknown star system gracing our skies for a few precious months. Press releases from astronomical institutions spoke of a wonderful opportunity to study a pristine piece of another solar system's building blocks. Here was a chance to analyze the raw material from which alien worlds might be born, delivered directly to our doorstep. Unlike the confounding Oumuamua 3.1, Atlas seemed to be an open book. It was behaving just as our theories said a comet should. It was following the script. There was an established sense of order, a feeling that we were beginning to understand the rules of this new and extraordinary game. We had found the first interstellar object, and it was a shock. We had found the second, and it was a reassurance. Now we had found the third, and it was becoming a routine. The astronomical community settled in for the show. This was not a frantic scramble for data like Oumuamua, which was already heading away from us when we found it. This was a slow, majestic procession. We had found 3I, Atlas, far out, giving us months to prepare to watch its every move as it made its grand entrance. Every major observatory had scheduled observation time. The Hubble Space Telescope and the James Webb Space Telescope were preparing to turn their powerful gazes upon it, ready to dissect its light with unparalleled clarity. Everything was proceeding with the calm, methodical precision of modern science. The expectation was one of incremental discovery, of filling in the details on a picture whose outline we already knew. We were watching a comet, a special comet, an ambassador from an unknown realm, but a comet nonetheless. We believed we understood the forces at play, the simple, elegant dance between solar radiation, frozen ices, and the immutable laws of gravity. But the universe is rarely so accommodating to our assumptions. Deep within the frozen heart of that distant traveller, a story was being written that had no precedent in our textbooks. The object we were watching, the object we thought we understood, was approaching a moment of profound transformation. The calm, predictable journey of 3I, Atlas, was about to be interrupted by an event so precise, so symmetrical, and so utterly bizarre that it would force us to question everything we thought we knew about the visitors who wander between. the stars. The open book was about to slam shut, replaced by a puzzle box of impossible geometry, and so for months its silent passage was a testament to celestial mechanics. A lonely pilgrim from a forgotten star, 3I, Atlas, arced through our solar system with the clockwork precision we have come to expect from the heavens. Across the globe, a silent army of watchers tracked its every move. From the high, dry deserts of Chile to the volcanic peaks of Hawaii, and in the cold, perfect vacuum of space where our most powerful eyes reside, the consensus was unanimous. The object was behaving perfectly. Its trajectory calculated and recalculated with obsessive accuracy, held true to the elegant laws of gravity Newton and Einstein had gifted us. It was a simple point of light, a visitor conforming to every prediction, a satisfyingly straightforward problem for the astronomical community. The initial flurry of excitement that had accompanied its discovery, that electric thrill of greeting a true alien, had settled into a quiet, studious observation. This was now the patient, methodical work of science, gathering data, refining orbits, and characterizing its physical nature. We thought we were simply writing a footnote in the story of interstellar visitors. We believed we knew what we were looking at, but the universe, it seems, rarely tells its most profound stories so plainly. The first hint that something was amiss was not a shout but a whisper, a faint, almost imperceptible murmur in the river of data flowing from the stars. It came from the object's light curve, the rhythmic pulse of its reflected sunlight. For any rotating, irregularly shaped body hurtling through space, this light curve is its unique fingerprint, its gravitational heartbeat. As it tumbles end over end, it presents different facets to our telescopes, causing its brightness to wax and wane in a predictable repeating pattern. For weeks, the rhythm of 3I, Atlas, had been as steady as a metronome, then a flicker. A tiny momentary stutter in the graph, so small that it was initially flagged by the computer algorithms as corrupted data and instrumental glitch. In an observatory in Arizona, an automated filter discarded the data point. In South Africa, a graduate student reviewing the nightly observations made a note of possible atmospheric distortion and moved on. These were the kinds of ghosts that haunt every astronomical campaign, the phantoms of technology and terrestrial interference. No one thought anything of it. You see these artifacts all the time, but the phantom refused to be exorcised. The next night, the flicker appeared again, this time in data from Spain, and then from Australia. The same subtle, maddening hiccup in the object's rhythm. It was too consistent to be random noise, too widespread to be a local error. The whisper was growing louder, becoming a nagging question in the back of the minds of the few specialists who stared at these meticulous graphs day after day. Emails began to circulate cautiously at first. Are you seeing a slight deviation around phase 0.7 inches? Your photometry. The replies trickled in, confirming the anomaly. The ghost in the machine was not in one machine, it was in all of them. It was coming from the object itself. This was the first thread to be pulled from the tapestry of our understanding, and with it the entire picture began to slowly, inexorably unravel. With the light curve now under intense scrutiny, astronomers turned their attention to another fundamental property, the object's overall brightness. Here too, the comfortable narrative began to fray. According to every model, as 3I Atlas approached the Sun, it should have brightened smoothly and predictably, a gentle, continuous crescendo. If it were a comet, sublimating ice would create a growing coma of gas and dust, causing it to flare in a well-understood manner. If it were a bare asteroid, its brightness would simply increase as a function of its decreasing distance from us and the Sunday. But 3I Atlas was adhering to neither script. Its brightening was erratic, punctuated by baffling short-lived surges. For a few hours it would shine with an intensity that defied its position, only to inexplicably dim again, falling below its predicted magnitude. It was as if a celestial dimmer switch was being played with a phenomenon with no clear physical cause. These were not the explosive, chaotic outbursts of a fragmenting comet, which would leave a lingering trail of debris. These were clean, surgical pulses of light, appearing and vanishing without a trace. The community was now officially puzzled. The initial dismissal had melted away, replaced by a growing, thrilling unease. This was no longer a routine observation. It was a developing mystery. Video conferences were hastily arranged, spanning continents and time zones. Faces illuminated by the glow of their monitors stared at each other, sharing graphs that all told the same impossible story. Theories were proposed and just as quickly discarded. Could it be pockets of highly volatile ices like solid nitrogen or carbon monoxide exploding as they were exposed to the sun? Perhaps, but the energy releases were too uniform, too controlled. Could its surface be composed of a strange mirrored material, creating moments of intense specular reflection as it tumbled? An intriguing idea, but it couldn't fully explain the synchronized dimming. Every natural explanation we could conjure felt inadequate, like trying to describe a symphony with only a single note. We were missing a crucial part of the composition. The final and perhaps most perplexing piece of the puzzle came from the very soul of the object, its spectrum. By passing its faint reflected light through a prism, astronomers can decipher its chemical makeup, reading the unique barcode imprinted on the light by the elements on its surface. Spectroscopy is our most powerful tool for remote geology, allowing us to understand the composition of worlds we can never touch. The initial spectra of 3I, Atlas, were unremarkable, showing the faint signatures of silicates and carbon compounds, the common building blocks of rocky bodies throughout the cosmos. But as the brightness fluctuations intensified, the spectrum began to transform. New razor-thin absorption lines started to appear in the data, ghostly fingerprints that would linger for an hour or two before vanishing completely. These were not the broad, smeared signatures of a dusty cometary coma. They were crisp, specific, and deeply strange. Some teams identified faint traces of metals like nickel and iron, but in ratios that seemed unnatural, almost refined. More unsettling were the transient lines that no one could immediately identify, signatures that corresponded to no common astrophysical molecule or element. It was as if the object was momentarily venting a specific exotic gas, a material that had no business being on the surface of a simple asteroid or comet. The data was undeniable, confirmed by the most powerful spectrographs on and off the planet, but it made no physical sense. The object was actively changing its chemical signature from one hour to the next. The mystery had now deepened into a profound enigma. The quiet, predictable visitor had revealed itself to be a cosmic chameleon, an object that defied easy categorization and broke the rules we thought were universal. The global observation campaign intensified. Every available instrument was now pointed at this single, baffling speck of light. Time on the Hubble Space Telescope was redirected. The newly commissioned James Webb Space Telescope, with its unparalleled infrared vision, was tasked to stare into its heart. The Very Large Telescope in Chile began a round-the-clock monitoring program. The scientific community held its collective breath. They knew with a certainty that was both terrifying and exhilarating that something unprecedented was about to happen. The object was unstable. It was talking to us in a language of light and chemistry that we did not understand, and its whispers were building to a crescendo. The pivotal moment arrived on a Tuesday. It didn't come with a flash of light or a dramatic explosion visible to the naked eye. It arrived quietly as a stream of photons collected in the dead of night by a 4-meter telescope perched on a lonely mountain. The data was piped across the world to a processing center in Germany, where a sophisticated algorithm performed the routine work of cleaning the image, removing cosmic ray hits, and adjusting for atmospheric wobble. An astronomer, bleary-eyed from a long night of monitoring, was performing the final visual check before archiving the observation. She expected to see what she had seen 1,000 times before, a single, overexposed star-like point, perhaps with a faint haze around it. She blinked. She zoomed in on the image. Her heart began to pound. She ran the calibration software again, thinking it must be an error, a flaw in the telescope's optics, a ghost reflection in the instrument. The result was the same. Frantically, she pulled up the data from the previous night. A single point. She pulled up the data from an hour earlier from a telescope in Hawaii. A single point. But on her screen in this image taken just minutes ago, there was not one object. There were three. Three perfectly distinct, impossibly crisp points of light, where just moments before there had been only one. A frantic message was sent out on an encrypted network used by the core teams ERGAEG end. Check Atlas. We have multiple components. Within the hour, the confirmation came flooding in. Hubble saw it. Webb saw it. Keck saw it. The world's observatories, in a moment of stunning unified discovery, all witnessed the same unbelievable sight. 3I Atlas was no longer a single entity. But this was not the chaotic, messy death of a comet. When comet Shoemaker-Levy 9 was torn apart by Jupiter's gravity, it disintegrated into a string of 24 fragments of all shapes and sizes, a string of pearls made of rock and ice, a beautiful but violent spectacle of nature. That is what fragmentation looks like. It is messy, it is random, it is explosive. This was something else entirely. This was clean. The images that now populated screens in control rooms around the world showed a breathtaking, almost unnerving degree of precision. 3 objects flying in a tight, stable triangular formation. They were not tumbling away from each other in a chaotic spray. They were locked in a delicate gravitational dance, orbiting a common center of mass as if they had been doing it for millennia. And as the first rapid spectroscopic analyses came back, the mystery deepened into absurdity. The 3 objects were not just visually distinct, they were nearly identical. Each component shared the same spectral signature, the same bizarre fluctuating chemistry. Each had almost precisely the same brightness, implying they were of equal size and mass. This was not a fragmentation. A fragmentation is a shattering. This was a division, a separation, a kind of celestial mitosis. It was as if an impossibly advanced cosmic scalpel had trisected the original object with surgical precision, leaving behind 3 perfect self-contained copies. Every model of cometary physics, every simulation of asteroid stress fractures, every theory we had for how objects break up in space was instantly rendered obsolete. They could not account for this. Nature does not work with this kind of symmetry. Gravity, when it tears things apart, is a blunt instrument. It is a hammer, not a blade. The shockwave of this discovery rippled through the astronomical world. The frantic excitement of the past weeks was replaced by a profound, humbling silence. A silence filled with the weight of a single, terrifying, exhilarating question that no one yet dared to ask out loud. We had been watching a lonely pilgrim, a simple, natural wanderer from another star. Now we were faced with a synchronized, perfectly formed triad of objects, moving with the grace and precision of a choreographed ballet. The rulebook had not just been rewritten, it had been torn from our hands and set ablaze. We were staring into an abyss of the unknown, and for the first time, we had to confront the staggering possibility that what was staring back was not the product of mindless physics, but of a deliberate, incomprehensible design. But the spectacle of its division was only the prelude. The true mystery was not that 3I Atlas had come apart, for comets are fragile wanderers prone to the gravitational whims and thermal shocks of the inner solar system. We had seen this before. Shoemaker-Levy 9, torn to shreds by Jupiter's might, had become a string of pearls before its final fiery plunge. Comet 73P, slowly disintegrating over years, offered a textbook example of a body crumbling under the sun's relentless gaze. We had our models, our frameworks for celestial death. We thought we knew the story, and so the vigil began. A global network of eyes, both robotic and human, all turned toward the 3 nascent glimmers of light, where one had been just hours before. The initial objective was simple, almost routine, to characterize the debris field. Astronomers sought to map the aftermath, to measure the spread of the fragments, to analyze their tumbling rotation and the fresh, pristine material now exposed to sunlight for the first time in millennia. It was an autopsy conducted from 100 million miles away, and every expectation was that we would find chaos. We were looking for the cosmic equivalent of a shattered vase, a large central piece perhaps, surrounded by a cloud of smaller irregular shards and a halo of dust, each piece sent careening on a slightly different path by the unpredictable energies of the breakup. The first streams of data painted a confusing picture. Spectrographs tasting the sunlight reflected from the new surfaces returned readings that were not merely similar but virtually indistinguishable from one another. Each of the 3 primary fragments was a perfect spectral echo of its siblings, suggesting an almost unbelievable homogeneity in their composition. There were no unexpected pockets of volatiles, no variations in mineral content that would indicate a layered or composite internal structure. It was as if the object had been carved from a single uniform block of primordial material, a finding that was unusual but not yet impossible. Perhaps 3I, Atlas, was just a remarkably well-mixed specimen from the Oort cloud's ancient nursery, but this was only the first thread in a tapestry of impossibility that was starting to be woven. Then came the photometry, the precise measurement of their brightness over time. As the fragments spun their light curves, the rhythmic rise and fall of their reflected sunlight should have been jagged and erratic, the signature of irregularly shaped tumbling rocks. Instead, the signals that reached Earth were smooth, periodic, and uncannily synchronized. They were not tumbling chaotically, they were rotating with a stately, almost disciplined grace. And more than that, the light curves for all three pieces were identical. Not just similar, identical. This implied something that sent a tremor of disbelief through the community. The fragments were not just of the same material, they were, against all logic, the same shape and size. This couldn't be right. It had to be an artifact, a misinterpretation of the data, a ghost in the machine. Teams on different continents using different instruments and different analytical software reran their calculations. They accounted for solar wind pressure for outgassing jets for observational biases. They sharpened their focus using adaptive optics to cut through the blur of our own atmosphere and tasked space-based observatories for an uninterrupted crystal-clear view. The answer that came back was immutable, a stubborn fact that refused to yield to skepticism. The three objects designated Atlas, A, B, and C were perfect triplets. To the limits of our most sensitive instruments, they were equal in mass, identical in shape, each a softly faceted ovoid, and most unnervingly of all, their initial velocity vectors were symmetrically perfect. They weren't blasted apart, they had simply separated. They were moving away from a common center of mass, not with the violent, haphazard energy of an explosion, but with the gentle equivalent push of a planned release. Imagine holding a perfectly spherical crystal in your hands, one that suddenly and silently separates into three equal, flawless segments, each segment gliding away from the others with the same serene, unhurried velocity. What you would feel in that moment is a fraction of the profound intellectual shock that now rippled through the world's observatories. The autopsy had revealed that the deceased was not the victim of a random accident. The evidence pointed towards something else entirely. Something ordered, something clean, something impossible. And with this single consolidated realization, the entire foundation of cometary science cracked. Every known natural mechanism for disintegration was in an instant rendered obsolete. Consider the prime suspect tidal forces. If 3I Atlas had strayed too close to a massive body like the Sun or a planet, gravity would have stretched it, pulling harder on the near side than the far side. This process, known as spaghettification, is an act of cosmic torture. It doesn't cleave, it tears. It would have ripped the comet into a messy trail of uneven fragments, a collection of large chunks and small bits like a loaf of bread torn apart by hand. The result we witnessed bore no resemblance to this brutal asymmetrical process. So we looked to the next culprit, thermal stress. As the icy body approached the Sun, the rapid heating of its surface could create immense internal pressures, causing it to fracture like a glass of ice water poured into a furnace. But such a fracture follows the path of least resistance. It seeks out internal fault lines, structural weaknesses, and veins of volatile ice that sublimate first. The result would be jagged, irregular pieces, a celestial shattering defined by pre-existing imperfections. The pristine, identical ovoids of Atlas were the antithesis of such a chaotic event. They looked less like a shattered rock and more like a cut diamond. What about a collision? Could it have been struck by a small, unseen asteroid? Physics is unforgiving on this point. An impact is a point source event. Energy is transferred at a specific location, creating a crater, a spray of ejecta, and sending shards flying in a cone of debris. It is asymmetric by its very nature. To get three equal pieces moving apart with such perfect symmetry would require an impact event so precisely engineered, so impossibly choreographed, that it belonged in the realm of science fiction, not observational astronomy. We even considered rotational stress, the possibility that the comet was spinning so fast it simply flew apart. Yet again, the physics failed us. A rotational breakup would have flung material off from the equator, likely creating two primary lobes connected by a thinning tether of material before they finally separated, along with a spray of smaller debris. It could not, produce three identical components in a clean, planar separation. Every single page in our textbook, every accepted model, every theory honed over centuries of watching the skies was thrown out the window. The scientific community was left standing in a conceptual void, holding a set of observations that, according to everything we knew, should not exist. The silence of initial shock was quickly replaced by a deafening roar of debate. Digital forums, academic listservs, and virtual conferences ignited with a firestorm of speculation. Papers were written and retracted within days. Reputations were staked on theories that seemed wild, even desperate. The problem was no longer simply explaining a comet's breakup. It was explaining a miracle of celestial geometry. It was like finding a river that flowed uphill or a snowflake with four sides. The observation itself was a direct assault on the known laws of physics as they applied to macrophysical bodies. We had to invent new science just to begin formulating a hypothesis. The first wave of radical theories focused on exotic material science. Perhaps 3I, Atlas, was not a comet in the conventional sense at all. Maybe it wasn't a loose agglomeration of ice and rock, but something far stranger. Theorists proposed it could be a single continent-sized crystal, a monocrystalline body of some unknown material formed in the unimaginable cold and pressure of an alien protoplanetary disk. Such a perfect crystal, if it possessed a uniform lattice structure throughout its entire volume, could potentially fracture along its cleavage planes with surgical precision when subjected to a specific uniform stress. It was a tantalizing idea, but it begged the question, a crystal of what? Nothing we know of could form a stable crystal of that magnitude. It would require a material with properties so far beyond our understanding that it might as well have been magic. Another branch of thought delved into even more esoteric territory, new states of matter. Could this object have been composed of something that wasn't quite solid, liquid, or gas? Some physicists explored the possibility of a Bose-Einstein condensate on a cosmic scale, a bizarre state of matter where trillions of atoms act in perfect quantum unison as if they were a single superatom. In theory, if such a macroscopic quantum object were to decohere or transition to a normal state, it might do so in a highly ordered, symmetrical fashion. The idea was breathtaking in its audacity, proposing that we had stumbled upon a manifestation of the universe's most delicate and strange quantum rules scaled up to the size of a mountain. It was a theory born of desperation, a grasp for an explanation in the deepest, most unexplored corners of physics. But it was a theory that some were willing to entertain because the alternative was even more unsettling. Because as every natural explanation failed, as every attempt to ground the event in familiar physics dissolved into paradox, an uncomfortable, unspoken thought began to surface in the minds of many. It was a thought that astronomers are trained from their first day to resist a conclusion they are conditioned to avoid at all costs. But the data was relentless, and its implications were becoming undeniable. The thought was this: what if the process wasn't natural? The perfect symmetry, the clean separation, the identical components, these are not the hallmarks of nature. Nature is messy, chaotic, and gloriously imperfect. It is the jagged coastline, the fractal pattern of a lightning bolt, the turbulent eddies of a river. The kind of perfection we were witnessing in the disaggregation of 3I, Atlas, is almost exclusively the domain of two things: mathematics and intelligence. The event looked less like a geological fracture and more like a carefully executed engineering protocol. It was reminiscent of a multi-stage rocket jettisoning its boosters or a satellite deploying its solar arrays. The components didn't break, they disengaged. This was the precipice of a paradigm shift so profound it threatened to redefine our place in the cosmos. To even consider it felt like a betrayal of scientific objectivity, a slide into fantasy. Yet the scientific method demands that we follow the evidence wherever it leads. And the evidence was pointing toward a conclusion that was as terrifying as it was exhilarating. If this was an engineered event, what was the purpose? Was it a probe shedding its outer layers as it prepared for its final objective? Was it a self-replicating system, an interstellar seed pod activating upon its arrival in a new star system? Or perhaps something more biological, a crystalline life form undergoing a process of division, a form of asexual reproduction on a scale we could barely comprehend? Suddenly, the central question of our investigation was completely transformed. We were no longer asking, what happened to 3I Atlas? That question had been answered. It had separated into 3 perfect pieces. The new question, the one that now echoed in the halls of every university and research institute, was far more profound. It was a question that split into 2 terrifying intertwined parts. Times how times was it so perfect, and times why times. The object was no longer just a curiosity. It had become an omen. It was a statement delivered from the depths of interstellar space and written in a language of impossible physics. It told us that our understanding of the universe was not just incomplete, but that it might be fundamentally wrong. It suggested that processes we could not imagine were at play in the great darkness between the stars. The messenger had shattered, but in its place, it left not a ruin but a riddle. A perfectly formed 3-part question hanging in the void, each piece a testament to the depth of our own ignorance. And we, its accidental audience, were now compelled to find an answer, no matter how profoundly it might change us. The search for what 3I Atlas was made of had ended. The search for what at times meant times had just begun. And so the initial shockwave of discovery, that moment of shared global astonishment, began to recede. What rushed in to fill the void was something far more demanding, a challenge not of observation but of pure intellect. The image of those 3 identical siblings parading in perfect formation through the void was no longer just a beautiful cosmic mystery. It had become an accusation, a silent indictment of our understanding of the universe. For the men and women who had dedicated their lives to deciphering the celestial rulebook 3I Atlas was now a page written in a language they could not read its grammar, defying every law they held sacred. The question was no longer times what times it was, but times how asterisk. How in all the chaotic grandeur of the cosmos could something so exquisitely ordered come to be? The world's finest minds, armed with the most powerful computational engines ever conceived, turned their full attention to this singular problem. The hunt for an explanation had begun, a hunt that would push them to the very precipice of reason. Their first port of call was the familiar, the well-trodden ground of cometary physics. Comets, after all, are famously fragile. They are not solid, monolithic worlds, but loose agglomerations of ice, dust and rock held together by their own feeble gravity. They are cosmic snowballs prone to fragmentation under stress. The teams began with the most obvious culprit, tidal forces. We've seen this drama play out before, a gravitational tragedy in slow motion. A comet in its long, looping journey ventures too close to the colossal presence of the Sun or a giant planet like Jupiter. The immense gravitational pull of the larger body creates a differential, a cosmic tug-of-war across the comet's fragile frame. The side nearer the Titan is pulled more strongly than the far side, stretching and squeezing the object until its tenuous bonds can hold no longer. It shatters not in a violent explosion, but in a quiet, inexorable surrender to physics. This was the leading hypothesis, the most elegant and orthodox explanation. At supercomputing centers from Pasadena to Darmstadt, teams began constructing digital phantoms of 3I Atlas. They fed into their models every known variable, its estimated mass, its velocity, its trajectory, its chemical composition gleaned from the faint light of its coma. They programmed the unyielding laws of gravity, and then, in the simulated dark of the computer, they rewound time. They sent their digital comet hurtling back along its path, searching for the gravitational encounter, the close pass with a massive object that must have been its undoing. They ran thousands of simulations, millions of them. Each one a slight variation, a gentle tweak of the parameters. Perhaps its core was denser than they thought. Perhaps its trajectory was off by a fraction of an arc-second. They watched the virtual object swing past a virtual sun, a virtual Jupiter, even a hypothetical unseen brown dwarf lurking in the outer system. And every single time the model failed, the results were not just inconclusive, they were emphatically negative. The numbers painted a stark and unforgiving picture. For tidal forces to be the executioner 3I, Atlas would have needed to pass through a gravitational kill zone of immense power. Yet its known trajectory showed it had given the Sun a wide berth, staying far outside the orbit of Mars. It hadn't flirted with Jupiter or any other planet. Its path through the inner solar system was a stately conservative arc, devoid of the gravitational drama required for such a catastrophic breakup. The simulations showed that at its closest approach, the Sun's tidal pull on the object was less like a cosmic giant tearing it limb from limb, and more like a gentle breeze against a mountain. It wasn't nearly enough force to crack a fragile snowball, let alone cleave a monolithic body into 3 perfect industrial-grade components. The first and most logical door had not just been closed, it had been bricked over, leaving the researchers staring at a solid wall of impossibility. Frustration began to mount a low hum of intellectual dissonance in labs around the world. If gravity hadn't pulled it apart, then perhaps the object had torn itself apart from the inside. This led them to the second major theory of cometary demise: rotational stress. As a comet nears the Sun, the solar radiation heats its surface, causing ices to sublimate directly into gas. These jets of escaping gas can act like tiny, unpredictable thrusters, not only propelling the comet but also spinning it up. If the outgassing is uneven, it can impart a torque, causing the comet to rotate faster and faster. Imagine a figure skater pulling in their arms to accelerate their spin. The comet does the same, driven by its own internal activity. As the rotational velocity increases, centrifugal forces build from the core outwards, a relentless pressure straining the object's internal structure. Eventually, a critical threshold is reached. The force pulling it apart overwhelms the gravity holding it together. The comet disintegrates, flinging its constituent parts out into space. Here at last was a mechanism that didn't require an external accomplice. This was a story of self-destruction. The modelers returned to their consoles with renewed, if cautious, optimism. They began to spin their virtual versions of 3I, Atlas programming in asymmetric jets of gas to serve as the engine of its own breakup. They dialed up the rotational speeds, pushing the digital object faster and faster, seeking the breaking point. And it did break. In the simulations, the object would indeed fly apart, but the result was never what they saw through their telescopes. The simulated breakup was a chaotic, messy affair. The virtual comet would shed dust and pebbles from its equator, then split into a dozen uneven chunks of varying sizes, which would then crumble further into a cloud of debris. It was a cosmic demolition, not a surgical dissection. To get the simulation to produce anything even remotely resembling the observed reality, 3 clean equal fragments, the required starting conditions became absurd. The model demanded that the original object possess an internal structure of impossible symmetry. It needed to have 3 identical pre-existing fault lines, like score marks on a piece of glass, radiating from a perfectly central homogeneous core. The outgassing jets needed to be positioned with the precision of rocket nozzles firing in a perfectly balanced sequence to spin the object up on a stable axis without inducing any wobble. And the final fracture needed to occur in a single instantaneous moment across all 3 planes simultaneously. It was like demanding a spinning ball of clay on a potter's wheel spontaneously fracture into 3 identical perfectly formed vases. It wasn't physics anymore. It was a request for a miracle. Each successful simulation felt less like a discovery and more like a cheat, a scenario so finely tuned and improbable that it had a statistical likelihood of 0. The explanation was becoming more fantastical than the mystery it was meant to solve, and that is when the object began to mock them. As the weeks turned into months, a new set of bewildering data points started to trickle in. According to every model of cometary fragmentation, the pieces of a broken comet should begin to behave like pieces. They should start to tumble erratically, their spin axes shifting as gas jets fire unpredictably from newly exposed surfaces of fresh ice. They were expected to develop their own distinct irregular comas and tails, each a unique cloud of shedding material. And most importantly, they were expected to drift. Each fragment, having been cast off with a slightly different velocity, should begin a slow, inexorable separation, their pristine triangular formation gently dissolving into the background of space. This is the fate of all broken things in the cosmos. Order decays into chaos. But the children of 3i, Atlas, refused to follow the script. Their stability was unnatural. Using the world's most sensitive instruments, astronomers confirmed that the 3 fragments were not tumbling. They were rotating, yes, but with the sublime stability of gyroscopes, each spinning on a fixed, unwavering axis. Their comas were not the chaotic bursts of shedding ice one would expect from a fractured interior. Instead, they were faint, perfectly symmetrical, and most unnervingly appeared to pulse with a subtle shared rhythm. They were holding themselves together with an integrity that defied belief. Normal cometary fragments, like clumps of poorly packed snow, should have begun sublimating and disintegrating within days of the breakup. These objects, however, were behaving as if they were carved from solid iron, their sharp edges and defined forms remaining pristine against the relentless sandblasting of the solar wind. Then came the observation that tipped the scales from profound mystery to something approaching scientific dread. They weren't just holding their formation, they were actively managing it. The drift, the slow, expected separation wasn't happening. In fact, careful analysis of their positions over hundreds of observations revealed something that sent a chill through the community. The 3 objects were making tiny, almost imperceptible adjustments to their relative positions. It was not propulsion in the way we understand it. There were no visible plumes, no telltale ion trails. It was subtler than that. One fragment would slow its orbital velocity by a few millimeters per second, while another would speed up, maintaining their equilateral triangle with a precision that orbital mechanics alone could not explain. It was as if they were connected by invisible elastic threads, constantly correcting for the minor perturbations of solar gravity to maintain their perfect ghostly dance. The formation wasn't a static relic of a past event, it was a dynamic, actively maintained system. Within the cloistered world of astrophysics and planetary science, the intellectual struggle began to curdle into a tense, unspoken conflict. The community quietly fractured into 2 camps, their debates spilling out of peer-reviewed journals and into hushed late-night conversations at conferences. On one side were the traditionalists, the defenders of known physics whom we might call the naturalists. Their public stance was one of calm confidence. Nature, they argued, is simply more imaginative than we are. There must be a novel, undiscovered physical mechanism at play, perhaps a bizarre form of electrostatic adhesion or a complex interplay of magnetic fields and sublimating charged dust. They proposed exotic internal structures, a solid crystalline core that cleaved perfectly along crystallographic planes, a phenomenon never before seen but theoretically possible. Their argument was a powerful appeal to scientific humility and to the principle of Occam's razor: do not invent extraordinary causes when an undiscovered but ordinary one might exist. They were the guardians of scientific conservatism, holding the line against what they saw as a dangerous slide into speculation. Their private reality, however, was one of deep frustration. Night after night they returned to their whiteboards and supercomputers, but every new idea, every exotic natural model, ultimately collapsed under the weight of the object's sheer persistent strangeness. On the other side were the provocateurs. This was a looser, younger, and more daring coalition of scientists, those willing to follow the data wherever it led, even if it led them off the map of established science. They weren't shouting aliens from the rooftops. Their arguments were far more nuanced, and in many ways more unsettling. They began to publish papers that didn't offer solutions, but instead rigorously demonstrated why all known natural solutions were impossible. Their work was a meticulous process of elimination. They systematically proved that tidal forces couldn't have done it. They proved that rotational stress couldn't have done it. They showed that the object's material strength had to be orders of magnitude higher than any known cometary nucleus. They demonstrated that the active station keeping of the fragments violated the conservation of momentum unless there was an unseen, impossibly efficient energy source at work. They weren't offering an alternative theory. They were simply stating with mathematical certainty that the object's behavior was inconsistent with the physical laws that govern collections of ice and rock. They were, in essence, positing that 3i Atlas was not a natural object in the conventional sense. This was the line they would not cross in public, the word they dared not speak, artifice, but the implication hung in the air, thick and suffocating. They were exploring the fringes of physics, discussing concepts like cohesive matter bound by forces other than gravity, or speculating that the breakup wasn't a failure at all but a deployment, a deliberate, controlled separation. These ideas were met with fierce resistance from the naturalist camp. Papers were rejected, conference invitations were withheld. The collaborative spirit of the scientific endeavor was beginning to fray, replaced by a deep and uncomfortable schism. You were either searching for a new law of nature, or you were accepting that you had encountered something that transcended it. This was no longer a simple astronomical observation. It had become a profound philosophical crisis, a direct challenge to our most fundamental assumption that the universe is ultimately comprehensible, a place of random, chaotic, yet fundamentally natural processes. 3I, Atlas, suggested another possibility. It suggested that order, complexity, and even intent might not be the exclusive domain of life on Earth. The three perfect pieces were no longer just a scientific puzzle. They were a mirror reflecting our own deepest hopes and fears about our place in the cosmos. Were we witnessing an unknown, magnificent new aspect of nature's creative power, or were we, for the first time in human history, staring at a signpost, a deliberate message left in the dark, patiently waiting for someone to finally read? The deadlock was complete, the tension stretched to its breaking point. The world's greatest thinkers were stumped, caught between an explanation that was impossible and an alternative that was unthinkable. All they could do was continue to watch, to gather more data, and to wait for the object to make its next move. And they would not have to wait for long. The silence from the abyss had been the defining feature of our long vigil. For months we listened to the three children of 3I, Atlas. We watched them tumble with impossible grace through the void, but the cosmos in its vast indifference offered no sound, no explanation. Every theory had crumbled to dust, every model had shattered against the facts. We were adrift, lost in a sea of questions with no shore in sight. And then, after 184 days of profound quiet, a whisper. It wasn't a transmission in any sense we recognized. Not a radio burst, not a coded message, not the chaotic hiss of a quasar. This was something else entirely, a ghost in the cosmic static. Buried deep within the microwave spectrum, a signal so faint, so delicate, it was initially dismissed as a calibration error in the Atacama Large Millimeter Array. But the error refused to disappear. It persisted, a stubborn, ethereal hum, emanating not from one fragment, but from all three, and they were singing in perfect resonant harmony. This wasn't the sound of nature as we had ever understood it. Natural phenomena are messy, chaotic, governed by the beautiful but brutal laws of entropy. A star roars, a magnetar screams, a black hole collision sends out a gravitational clang. This signal, however, possessed an architectural precision, a mathematical purity that felt less like physics and more like music theory. It was a chord, an impossibly complex chord, of electromagnetic energy with harmonics and overtones layered with a composer's intent. Each of the three fragments was broadcasting on a fundamental frequency, but they were phase-locked, interconnected like three celestial tuning forks. When one waveform crested, the others crested in precise mathematical relation. They were entangled by this invisible symphony, a single coherent entity, despite the thousands of kilometers now separating their bodies. This discovery did not solve the mystery. It plunged it into a far deeper, more terrifying dimension of the unknown. Because a signal this organized, this stable, this structured implied one of two staggering possibilities. Either it was the product of an advanced non-human intelligence, a technology so far beyond our own that we were like ants listening to a sonata, or we were witnessing an entirely new law of physics, a phenomenon of matter that had remained hidden from us since the dawn of time. Both prospects were equally revolutionary and equally frightening. The world's brightest minds descended upon this single spectral enigma. Cryptographers searched for patterns for language, but found none. Astrophysicists tried to model it as some bizarre plasma interaction, but the numbers refused to align. It was a lock without a key, a message without a known alphabet. The The breakthrough, when it came, didn't arrive from looking outward at the signal, but by looking inward at the very nature of matter itself. In a quiet, unassuming laboratory in Kyoto, a computational materials scientist, Dr. Aris Thorne, was working on a radical and controversial hypothesis. He had long believed that under extreme conditions of cold and pressure, exotic matter could achieve a state of self-organization far beyond simple crystallization. He called it quantum templating, the idea that a precise resonant energy field could act as a blueprint, forcing atoms to arrange themselves not into random lattices, but into complex macro-scale functional structures. It was a theory that existed at the wild frontier of science, bordering on philosophy. His colleagues were skeptical, his funding requests often denied. For years, his complex simulations had produced nothing but digital noise. But when his team fed the precise frequencies and harmonic data from 3i, Atlas, into their most powerful simulation, something utterly transformative happened. They weren't trying to decode the signal as a message, they were using it as an instruction set, a command. The simulation began as always with a virtual cloud of elements believed to constitute the original parent body of 3i, Atlas. Silicates, carbon compounds, water, ice, and trace amounts of metallic elements all suspended in the simulated vacuum of deep space. For the first 72 hours of the simulation, nothing happened. The virtual matter swirled chaotically, a primordial soup of digital dust. The team watched their hopes diminishing with every passing hour. Thorne himself felt the familiar sting of failure, another dead end. But then, the program, guided by the phantom frequencies from the real object, began to weave its magic. The virtual energy field, a perfect digital echo of the signal from space, permeated the cloud. And the cloud responded. It was like watching a ghost assemble its own skeleton. Individual atoms, compelled by resonant forces, began to lock into place. They didn't form a simple crystal. They formed an intricate three-dimensional lattice of impossible complexity, a web of interconnected filaments and nodes that grew from the inside out. What emerged on the screen was not a dead rock. It was a machine, a vast geologic circuit board taking shape. The simulation was building atom by atom the internal structure of 3i, Atlas. It was a moment of profound world-altering revelation. The signal wasn't a times byproduct times of the object. It was the object's times operating system asterisk. But the most breathtaking moment was yet to come. Once the virtual object was fully formed, a perfect digital twin of the original, the simulation introduced the next phase of the energy signature. A subtle shift in the harmonics, a change in the resonant chord. It was a command for division. On the screen, deep within the object's core, 3 distinct resonant nodes began to glow. These nodes acted like gravitational scalpels, vibrating at an intense frequency. The intricate bonds of the crystalline lattice did not shatter or explode. That would have been too crude, too chaotic. Instead, they began to unweave. The filaments disconnected with surgical precision along predefined pathways. The great machine was disassembling itself from within. The simulation showed 3 perfect shear planes, forming not through brute force, but through a resonant decoupling of the object's fundamental structure. It was like a zipper being undone on a cosmic scale, and as we watched, holding our collective breath, the single virtual object calmly, cleanly, and flawlessly separated into 3 identical pieces. They drifted apart on the screen, each one a perfect smaller copy of the whole, leaving behind no debris, no dust, no trace of violence. The simulation had perfectly replicated the impossible fracture, the mystery of times, how times was solved. 3i, Atlas, hadn't been broken. It had been programmed to divide. A simulation, no matter how perfect, is not proof. It's a map, a breathtakingly elegant map, but one that still required confirmation in the real world. Did the fragments of 3i, Atlas, truly possess this bizarre crystalline interior, or was Thorne's simulation just a beautiful coincidence, a mathematical ghost? The question sent a new urgency, rippling through the astronomical community. We had to see inside. This was a task that pushed our technology to its absolute limit. The fragments were too distant, too small for any single telescope to resolve their interiors. It would require a global effort, a planetary collaboration of unprecedented scale. Telescopes across every continent, from the high deserts of Chile to the volcanic peaks of Hawaii, were linked together. Using a technique called very long baseline interferometry, they would combine their light, effectively turning the entire planet Earth into a single massive telescopic lens. Their target to penetrate the dusty comas of the fragments and map their internal density to see the unseeable. The preparations took weeks. Atmospheric conditions had to be perfect across the globe. The orbital mechanics had to be calculated to the microsecond. The sheer volume of data being collected was staggering petabytes of information flowing into supercomputing centers in Germany and the United States. For 7 long nights, the Earth stared with its one great eye at the enigmatic travelers. And then the agonizing process of data reconstruction began. It was like assembling a billion-piece jigsaw puzzle in the dark. Scientists and engineers worked in shifts, their faces illuminated by the glow of code. The world waited, suspended between a radical new reality and a return to baffling ignorance. The first image that resolved from the noise was of Fragment A. It flickered onto the main screen at the processing center, and a hush fell over the room. What we saw was not the homogeneous cratered interior of an asteroid or comet. It was a cathedral. Beneath the surface layer of ice and regolith lay a sight of stunning alien beauty. A vast, intricate scaffolding of crystalline filaments glowing faintly in infrared crisscrossed the object's interior. They formed a repeating geometric pattern, a fractal lattice that was both hauntingly biological and fiercely mechanical. It looked like a cross between a neuron and a superconductor. This was the structure Thorne's simulation had predicted, the skeletal framework of a natural machine. Images of fragments B and C soon followed, and they were identical. Each one possessed the same impossible internal architecture. We could even pinpoint the shear planes, the surfaces where the object had divided. They were unnaturally smooth, polished like cleaved diamond. There were no stress fractures, no rubble fields, just the clean, elegant lines of a deliberate programmed separation. The evidence was undeniable, staring back at us from the depths of space. 3I, Atlas, was not a piece of debris left over from the formation of the solar system. It was something else, something designed, something built. This discovery shattered the bedrock of our most fundamental definitions. We have always drawn a hard line between the living and the non-living, between biology and geology. One is complex, organized, and replicates. The other is simple, chaotic, and inert. But 3I, Atlas, existed in the vast, unexplored chasm between those two concepts. It wasn't alive in any biological sense. It had no cells, no DNA, no metabolism. Yet it possessed a level of structural complexity and behavioral sophistication that rivaled life itself. It followed a clear directive: travel, mature, and replicate. It was a self-propagating structure, a cosmic seed. But a seed for what? Not for life as we know it, not for carbon-based organisms or sprawling ecosystems. It was a seed for a different kind of ordering principle in the universe, a seed for complexity itself. A machine designed by the universe, or something in it, to spread structure, to carry a pattern, to imprint a design upon the cosmos. Perhaps it was a form of natural panspermia, but instead of seeding planets with biology, it was seeding empty space with the architecture of organized matter. It was a carrier of information written not in a genetic code, but in the resonant frequency of its own being. Its purpose was not to live, but to build. We had looked at 3I, Atlas, and seen a dead piece of rock. We couldn't have been more wrong. We were looking at a chrysalis, a vessel, an artifact of a process, so vast and so alien, it defies our imagination. The tripartite split was not its death, it was its birth. The birth of 3 new carriers of the code, now drifting apart on new trajectories, each one destined to continue the cycle. We had solved the puzzle of the immaculate fracture, a feat of scientific dedication that had redefined the boundaries of the possible. But in doing so, we had uncovered a far more profound and unsettling truth. We had found undeniable evidence of purpose in a universe we thought was random. The question was no longer times how times 3I Atlas split. We had answered that. The new question, the one that now keeps us awake at night as we watch the three silent messengers travel deeper into the darkness, is terrifyingly simple. What happens when they arrive at their destinations? And what exactly are they designed to build? And so we find ourselves here in the quiet aftermath, adrift in the cosmic wake of a visitor that refused to play by our rules. We are left staring into the void it departed, holding the phantom pieces of a puzzle that cannot be solved with the physics we currently know. All our models, all our elegant equations that describe the chaotic, magnificent violence of the cosmos fell silent in the face of its passage. They could not account for the serene geometric perfection of its end. The universe, we thought, was a place of entropy, of explosive fragmentation and gradual decay. But 3I, Atlas, showed us something else. It showed us order, precision, and an event so statistically impossible it borders on a miracle, forcing us to confront a profound and unsettling truth we know far, far less than we ever imagined. Our journey with this ghost from another star began with the familiar thrill of discovery. From that first unassuming point of light captured by the asteroid terrestrial impact last alert system, just another traveler on the interstellar ocean, we charted its path with growing excitement. We treated it as we had treated Oumuamua and Borisov, before it as a priceless sample of a distant solar system, a chemical messenger carrying secrets of its alien birthplace. We measured its chemistry, analyzed its trajectory, and built our comfortable narratives around it. Was it a nitrogen iceberg chipped from a Pluto-like world, a desiccated cometary nucleus on its final lonely orbit? These were the questions we knew how to ask the boxes we tried to fit it into. For a time, it seemed to cooperate, behaving like any other long-period comet waking from a deep slumber as it neared the warmth of our star. But this object was not a messenger, it was a test, and its story was not one of simple discovery but a relentless systematic dismantling of our cosmic certainty. The first crack in our understanding was the split itself. Comets fracture all the time, torn apart by tidal forces or thermal stress in spectacular chaotic displays. We expected a messy divorce, a cloud of rubble and dust marking a violent end. What we received instead was something akin to cosmic surgery. One object became three, each a pristine, geometrically ideal component of the original. There was no explosion, no shrapnel, no chaotic spray of debris that our laws of physics demand. It was a quiet, deliberate unfolding as if a celestial jeweler had taken a diamond to a cutting wheel. The telemetry that came back from our observatories painted a picture of impossible grace. Three identical fragments separating with velocities so finely tuned that they maintained a perfect, stable formation. They weren't tumbling, they were gliding, each piece a seemingly flawless shard of the whole, their pristine surfaces unmarred by the cataclysm that should have been their birth. It was less a fracture and more a revelation, a transformation from a singular entity into a trinity executed with a precision that nature in its glorious randomness has never been known to produce. This is where the true legacy of 3I, Atlas, begins, in the silent space between those three departing fragments. That uncanny perfection has become a wedge driven deep into the foundations of modern astrophysics. To explain it, we must venture far beyond the known shores of science. The conservation of momentum and energy, the bedrock principles of our physical reality, simply do not allow for such a clean break without an immense, perfectly directed and utterly invisible energy source. Where did the energy for this controlled separation come from? A conventional explosion, even one hidden deep within its core, would have sent debris flying in every direction, creating a pressure wave that would have scarred and spun the fragments. We saw none of that. We saw only a gentle, inexorable push, a phantom force, guiding each piece onto its new independent trajectory. This single observation forces us to entertain ideas once relegated to the furthest fringes of theoretical physics. Are there forms of energy storage and release that we have yet to comprehend? Could matter itself possess latent properties, an ability to transition between states in a way that generates directional force without combustion or kinetic violence? Theorists are now reluctantly dusting off concepts of contained vacuum energy, of controlled phase transitions in exotic matter, or even of localized manipulations of space-time. These are not comfortable ideas. They speak of a universe with physical laws more complex, more subtle, and perhaps more programmable than we have ever dared to believe. The split of 3I, Atlas, was not just a geological event, it was a physics problem, an equation written in light and motion across our sky, and the answer it demands is a new chapter in our understanding of everything. And what of the material itself? What substance could possibly withstand the eons-long journey through the harsh radiation of interstellar space, only to yield with such crystalline perfection? Every comet we have ever studied is a dirty snowball, a loose agglomeration of ice rock and dust. They are cosmic mud pies, inherently fragile and structurally impure. When they break, they crumble, but the fragments of Atlas were not crumbles, they were facets. This implies a structure of incredible uniformity, a monolithic crystal or a manufactured alloy of unimaginable strength and purity. To maintain its integrity across light years of travel and then fracture along 3 perfect cleavage planes suggests a material science so advanced it appears magical to us. Perhaps it was a single vast crystal grown not in the chaotic crush of a protoplanetary disk to which we are accustomed, but in the zero-gravity vacuum of deep space, allowing for a flawless atomic lattice. Or perhaps it was something else entirely. The clean, almost surgical surfaces of the fragments gleaming in the sun's light have ignited a firestorm of speculation about artificial origins. Could we have witnessed the deliberate division of a manufactured object, a probe, a vessel, or even a piece of galactic art designed to behave in this exact way upon entering a star system like ours? The thought is both thrilling, terrifying. It shifts the conversation from geology to engineering, from natural phenomena to intelligent design. The perfect split stops being a random act of nature and becomes a potential signal. It suggests an underlying blueprint, a purposefulness that chaos simply cannot create. The object's journey is no longer a simple gravitational slingshot, but a potential delivery. We are forced to ask, was this fracture a failure or was it a function? Was it breaking apart or was it activating? This leads us to the most profound possibility of all, that the event was not just precise, but that it contained information. In information theory, complexity and order are the hallmarks of a message. The chaotic static of a radio contains little information, but the structured, ordered waveform of a voice contains a wealth of it. The messy, random explosion of a typical comet is cosmic static. The serene, ordered, symmetrical fission of 3I. Atlas, however, is a structured waveform. It's a signal. The 3 identical pieces, the specific velocities, the stable formation, these parameters could be variables in a complex equation. A message not written in radio waves, but in the language of orbital mechanics and physics itself. It could be a beacon, a calling card, or a warning. It might even be a galactic survey marker deploying smaller units to observe our system from different vantage points. By this interpretation, we weren't just watching a comet die. We were witnessing the unpacking of a parcel that had been in transit for millennia, a parcel whose contents we are only now beginning to fathom. The legacy of 3I, Atlas, therefore, is not an answer. It is a question whispered across the void that has irrevocably altered the scientific landscape. It has transformed the search for interstellar objects from a niche astronomical curiosity into a top-tier priority for the survival and understanding of our species. We can no longer be content to simply spot these visitors as they fly past. We must be prepared to intercept them. Projects that were once theoretical exercises like missions to chase down future interstellar travelers are now being discussed with a newfound, desperate urgency. We need to get up close to touch these objects, to analyze their substance before they reveal their secrets and vanish back into the darkness. This singular event has also breathed new life into the search for extraterrestrial intelligence. For decades, SETI has been defined by the ear, by vast radio dishes listening for faint whispers from distant stars. We have been waiting for a phone call. 3I, Atlas, suggests we should have been watching the mailbox instead. Perhaps the most efficient way to communicate across the galaxy is not through ephemeral energy waves which dissipate and get lost in the noise, but through physical artifacts. Messages in a bottle cast into the great cosmic ocean designed to last for eons and to reveal their nature only to civilizations capable of observing them with sufficient care. It forces us to consider that the ultimate test of a species' intelligence might not be whether it can build a radio telescope, but whether it can recognize an intelligently designed object passing through its own celestial backyard. The great silence we've been listening for might not be empty at all. It might simply be quiet because the most advanced cultures communicate through the silent, patient language of matter and motion. And so we must re-evaluate everything. Every anomalous glint of light, every object that deviates slightly from its predicted path, must now be scrutinized with the suspicion that it could be another clue. The Vera C. Rubin Observatory, soon to come online in Chile, will be our new sentinel. Its all-seeing eye will scan the entire visible sky every few nights, creating a motion picture of the cosmos with unprecedented depth and speed. It is projected to discover dozens, perhaps hundreds of interstellar objects every year. Among that coming flood of visitors, we will hunt for the next atlas. We will search for more impossibilities, for more travelers that defy our expectations. We are no longer just cataloguing the sky. We are searching for artifacts, for the fingerprints of minds far older and perhaps far wiser than our own. We are sifting the sands of the cosmos, looking for the glint of another manufactured key. Ultimately, the legacy of 3I, Atlas, is a profound lesson in humility. It arrived in our solar system as a mirror, reflecting back at us the vastness of our own ignorance. It showed us that the universe is not only stranger than we imagine, but stranger than we times imagine. We build our models, our grand theories of everything, on the tiny sliver of reality we are able to observe. We are like island dwellers who have studied a single lagoon and believe they understand the entire ocean. This object was a creature from the deep, a leviathan of physics that surfaced for a moment, showed us a glimpse of a completely different biological or technological kingdom, and then submerged back into the abyss. It proved that our lagoon is connected to something vaster, more complex, and infinitely more surprising. The 3 fragments are gone now. They have receded into the darkness, each on its own solitary journey back into the interstellar wilderness from which they came. They will never return. They are 3 silent outbound ships carrying with them the answer to the greatest riddle ever posed to humanity. Were they the product of an unknown natural law, a fluke of physics that we will one day understand and incorporate into our textbooks? Or were they something more, the calling card of an intelligence so advanced that it communicates by, reshaping matter and energy in ways that appear to us as miracles? We do not know. We may never know. But the not knowing has changed us forever. We are now a species awakened to a new and astonishing possibility. We look up at the same night sky, but we see it with new eyes. It is no longer a static backdrop of predictable clockwork motion. It is a dynamic arena, a place of profound mystery and untold potential where impossible things can and do happen. We are listening to the silence, but we are also watching the darkness between the stars with a newfound intensity, with a sense of anticipation, of hope, and of awe. The passage of 3I, Atlas, has left an indelible mark on the human spirit, reminding us that the greatest discoveries are not the ones that confirm what we know, but those that shatter it completely. The grandest adventure is not in finding the answers, but in discovering the right questions. And this visitor, this impossible trinity, has left us with the most beautiful and terrifying question of all. The question is no longer just, are we alone? But what other impossibilities are already on their way?